Chapter 4, General Vector Spaces, Section 4.1, Real Vector Spaces. Let V be an arbitrary non-empty set of objects in which two operations are defined, addition and multiplication by numbers called scalars. By addition, we mean a rule for associating with each pair of objects u and v in V an object u plus v, called the sum of u and v. So this is not necessarily going to be the same addition that we've seen thus far on vectors or on scalars. It could be an entirely new kind of concept of addition that we'll define when we talk about any particular vector space. By scalar multiplication, we mean a rule for associating with each scalar k and each object u and v an object ku called the scalar multiple of u by k. Similar to addition, we're redefining scalar multiplication in the context of whatever vector space we're talking about. If the following axioms are satisfied by all objects u, v, and w in V, and all scalars k and m, then we'll call V a vector space. So basically we have three ingredients to a vector space. We have some set V, we have some addition that we'll define, and we have some scalar multiplication that we'll define. If we have those things and they satisfy certain axioms, then we'll call that a vector space. So the axioms we have to satisfy are these 10 listed over here. We need the sum of any two elements in our vector space to also be in our vector space. So if we add two things and somehow we got something that wasn't already in there, then it wouldn't be a vector space. The addition, however we define it, has to be commutative. The addition, however we define it, has to be associative. We have to have some zero vector in our vector space such that we can add it to any vector and that vector will stay the same. We have to have some negative vector for every single vector in our vector space such that if we add a vector to its negative, we get the zero vector. We have to have scalar multiplication closed in our vector space so that anytime that we multiply a vector by a scalar, we get something that was already in our vector space. We have to have our distributive property satisfied over scalar multiplication and addition, and similarly distributive property if we add the scalars first. And we have to have our scalar multiplication associative, and the scalar 1 times any vector in the vector space has to be equal to itself. So let's do an example of a vector space. How about we let V consist of a single object, which we'll denote by 0 for the 0 vector, and we'll define 0 plus 0 to just be equal to 0, and k times 0 to equal 0. This would be our trivial vector space. Let's check that it actually is 1. So in order for this to actually be a vector space, we have to have that our sum of any two vectors is inside of our vector space. So let's look at what 0 plus 0 is. Well, by definition, that's 0. So that is inside V. So 1 is satisfied. The sum of any two vectors is indeed in V. Let's check that this thing is associative. Not associative, commutative first. So 0 plus 0, well, that's equal to 0, which is the same thing as 0 plus 0. If I change the order, it doesn't really matter. So definitely commutative. Let's look at associative now. So that's 0 plus 0 plus 0 in parentheses. Well, if I add up these guys in parentheses first, I'll just get 0. So that's the same thing as 0 plus 0. But this 0, I could rewrite as 0 plus 0 using our definition. So I could put that in parentheses and keep my other 0. And there we go, I just proved that it's associative. Okay, how about the 0 vector? Well, in this case, the 0 vector is kind of obvious, isn't it? The 0 vector is 0, since 0 plus 0 is going to equal 0, because any vector in here is just 0, is only one vector. Okay, the negative of 0 negative of 0, in this case will be 0, since again, if you add it to itself, you get 0. Okay, how about scalar multiplication? Well, any constant k times 0 is going to equal 0 by definition. 0 is in there. So all the scalar multiples are in there. Let's look at distributive property. So k times 0 plus 0. Well, this thing is just 0 by definition. So this is just k times 0, which is the same thing as saying k times 0 plus 0, because I can just add 0 and it will stay the same. So this is the same thing as saying k0 times, k0 plus k0, because 0 equals k0 by definition. Let's look at number 8. K plus m times 0 is equal to 0, because anything times 0 is 0 by definition, but that's the same thing as 0 plus 0, which is the same as any constant times 0 plus any other constant times 0. So it's distributive in both ways. Let's look at associativity. So we have k times m0, but that's just going to be 0, obviously. This is 0 times k is 0. So that's just the same thing as any constant times 0. So you could just make that constant km. And then last but not least, obviously if we take 1 times 0, we get 0. Okay, so this thing actually is a vector space since it's a set, it has some stuff in it. It satisfies our 10 axioms under the addition and scalar multiplication that were given. Let's do another one. How about if V is Rn, and we define the vector space operations to be the usual operations of addition and scalar multiplication. So the ones that we're used to, where we just take any vector u and v and just add their components together to get addition and multiply the scalar by each of the components to get scalar multiplication. So let's check that the sum of any of these vectors is in there. Well, that should be kind of obvious since the sum of any n tuples will always be an n tuple. So the sum is definitely going to be in this vector space. When you add them two together, you're not going to get let's say you had an ordered pair plus an ordered pair. Then you're not going to end up with something like an ordered triple out of that. You'll still get an ordered pair. Let's skip to 6 because it's basically the same reason. The scalar multiple of an n tuple is also an n tuple. And then all of the rest of the properties like addition, being commutative and associative and scalar multiplication, etc., they all follow from properties of vector addition and scalar multiplication as we defined them previously. So all these properties were given in theorem 3.11. That'll give us axioms 2, 3, 4, 5, 7, 8, and 9. So when we have previous theorems that relate to the addition and scalar multiplication that you're already given, then checking if something is a vector space is quite a bit faster. How about we let V consist of objects of the form u equals u1, u2 through un, and so on. Notice in this case, we keep going. So this is an infinite sequence of real numbers. We'll define two infinite sequences to be equal if their corresponding components are equal, and we define addition and scalar multiplication component-wise to be basically the same as it was before, except that we do it infinitely. How about we confirm that V with these operations is a vector space? By the way, in this case, V is called R infinity instead of Rn. So how about we check axiom number 1? So to check axiom number 1, we need to check that the sum of u plus v is actually going to be in R infinity. So let's write what u is. Well, u is u1, u2 through un, and v is v1, v2 through vn. So by definition, that's going to equal u1 plus v1, u2 plus v2, un plus vn, which is in R infinity because it's an object of this form, an infinite sequence of real numbers. Let's do number 2. We need to check that u plus v is v plus u. So we'll again write out u and v in terms of the components. This is what we'll do pretty often when checking for vector spaces, unless we have something else that we can rely on that we already checked. So we'll write u plus v is u1 plus v1, u2 plus v2, and so on. And that is the same thing as if we swap these guys, because these are inside the components is just addition, regular addition of scalars, which is just regular addition of real numbers, which is commutative. We already know it's commutative. So we can just swap those. So I'm swapping all the v's and u's. And that's just the same thing as if I took all of the v1s and wrote them as their own sequence. And I added that to the sequence of all of the u's. Okay, so that's just v plus u, exactly what we wanted. Let's check number 3. So we need to check associativity. So let's look at u plus v plus w. So we'll again write everything out. So we have for u, u1, u2, un, and we're going to add that to v1 plus w1, v2 plus w2, vn plus wn, which is the same thing as u1 plus v1 plus w1, u2 plus v2 plus w2, and so on until I get to un plus vn plus wn, and I keep going. So then we have associativity of addition of real numbers. Pretty much every property we prove is going to follow from a property that we already have for real numbers once we get into the nitty-gritty of the components. So I'll just rewrite each of the components using the associative property. I just need to get to un plus vn plus wn, and that is u plus v in parentheses plus w as desired. Next up, I have to check that the 0 isn't here. So I'll just take 0 to be the vector with a whole bunch of zeros for each of the components. So 0 plus u is just 0, 0, and so on. And that'll add to u1, u2, through un, and so on. So we get 0 plus u1, 0 plus u2, 0 plus, 0 plus un, etc. And 0 plus each of those using properties of real numbers is just u1, u2, un, which is u. Okay, good. So we have our 0 vector as desired. Let's check for our negative. U plus negative u. How about we let negative u just be the vector u with each of the components negated? So u is just u1, u2, un, and negative u will be negative u1, negative u2, negative un. It's kind of a natural choice. Basically the same thing we'd be doing for Rn. So we get, when we add these guys, u1 minus u1, u2 minus u2, etc. Okay, but that's just going to be the 0 vector, right? Just get tons of zeros. Okay, so that's satisfied. Let's do number 6. So let's take a constant times u. Well, that's just going to be k times u1, u2, through un, and so on. So we'll distribute the constant. We'll get ku1, ku2, kun, and that's in R infinity because each of the components is a real number. It's an infinite sequence of real numbers still. But we take k times u1 plus, or actually, sorry, just u. I'm not looking at the components yet. So k times u plus v. And by the definition we were given, that's just k times u1 plus v1, u2 plus v2, and so on. Oops, I have to keep going. It's infinite after all. So that's k times u1 plus k times v1, because we can distribute, because these are all real numbers now. So k times u2 plus k times v2, k times un plus k times vn, which is just ku plus kv. Okay, so that distributive property works. Let's look at the other one. So we have k plus m times u, but that's just k plus m times u1, u2, un. So that's k times u1 plus m times u1, because again, distributive property over regular addition. ku2 plus mu2, kun plus mun, and that's just ku plus mu. Okay, almost done. We have to check now that the scalar multiplication is associative. So let's look at k times mu. So that's k times mu1, mu2, mun, and that's k mu1, k mu2, k mun, which is just k mu. Okay, last one is to check that 1 times u is still u, but even though it's obvious, we'll still check it. We have 1 times u1, 1 times u2, 1 times un. That, when you take 1 times anything, when you're scaling, you just get itself. So u1, u2 through un is what we get. And that's just u. Okay, perfect. So this thing actually is a vector space because it has the 3 components and they satisfy the 10 axioms. A lot of work to check when you have to go through each of them and write each in terms of the components, but it is a very effective way of doing it. As another example, how about we let V be the set of 2x2 matrices with real entries, and we'll take the vector space operations on V to be the usual operations of matrix addition and scalar multiplication. So again, we'll just add the components inside the matrices, and that's how we'll get our addition, and we'll just scale the components to get our scalar multiplication. So let's confirm that V with these operations is a vector space. So for number 1, remember the sum of any 2x2 matrices is also going to be a 2x2 matrix. So that satisfies axiom 1. The sum is still going to be a 2x2 matrix. Can't end up with a 3x3 if you're just adding 2x2s. So then for number 2, that's the commutative property. We have a theorem that was 1.4.1 part A. Told us that adding matrices is commutative. We have the same theorem but part B for associativity. Should make sense because addition for real numbers is associative and we're just going to the components similar to last time anyway. For number 4, how about we just take the 0 vector to be the 2x2 0 matrix with 4 zeros. So that means that if we take 0 plus any vector u, that's just going to be the 2x2 matrix of zeros added to some matrix with arbitrary components u11, u12, u21, u22, and when you add it, you get 0 plus u11 is just going to be u11, 0 plus u12 is just going to be u12, 0 plus u21 is just u21, and 0 plus u22 is just u22. So we do get back our vector u. To check number 5, negative u. We need that to be something that will cancel out u, so how about we just make it the same matrix but with each component negated. So negative u11, negative u21, negative u12, and negative u22. Let's test that by adding it to u. So we take u plus negative u, we get u11, u21, u12, u22 for u, plus negative u11, negative u12, negative u21, negative u22. And that does end up being the vector of zeros, because each of the components will cancel, so that's the 0 vector, exactly as we desired. All right, only have 5 more axioms to check. So for number 6, it's going to be the same as number 1 pretty much. Remember the scalar multiple of a 2x2 matrix is still a 2x2 matrix. For number 7, for the scalar multiplication matrix properties, we can still use that theorem 1.4.1, gave us all these properties. So this was part H for axiom 7, and then for axiom 8, it was part J. For axiom 9, it was part E, so that'll save us a little time. And then for number 10, we just have to check that 1 times u is still going to be u. So notice that's just going to be 1 times u11, u12, u21, u22, which is just 1 times each of the components. So we just get u11, u12, u21, u22, which is just u. So this thing is a vector space. Let's do another example. How about we confirm that the set V of all m by n matrices with the usual matrix operations of addition and scalar multiplication is a vector space. So notice we have addition and scalar multiplication. Those will just produce n by n matrices, same as before with the 2x2s. So axioms 1 and 6 will follow for the same reasoning as before. Then notice we used theorem 1.4.1 for most of the other ones. For this one, we just have to find 0 as an n by n matrix with all 0 entries, the negative as an n by n matrix with all negative entries, and then 1 times it, again, will follow the same reasoning. So all of the remaining axioms follow from the same as the previous example. So the remaining axioms follow similarly to the example 4 that we just did. So save us a little bit of time. Let's let V now be the set of real valued functions that are defined at each x in the interval from -infinity to infinity. If f equals f of x and g equals g of x are 2 functions in V, and if k is any scalar, then we'll define the operations of addition and scalar multiplication by regular addition of functions that you would imagine, and scalar multiplication of functions. Let's confirm that V with these operations is a vector space. Okay, so how about we check axiom number 1. Notice that adding a function to another function couldn't make the function that you get undefined in any way. So the sum of functions defined at each x in the interval from -infinity to infinity are still going to be defined at each x in that interval. Okay, let's look at number 2. If we take f plus g, we want to see that that equals g plus f. So by definition, that's f of x plus g of x. So that's the same as writing g of x plus f of x, because addition of functions is commutative. So that's g plus f. For number 3, if I have f plus g plus h, that's the same as saying f of x plus g of x plus h of x. So that's equal to f of x plus g of x added to h of x, because addition of functions is associative. So that's just f plus g plus h. For number 4, how about we let our 0 vector be the function f of x equals 0. So it's the function that's always 0, the constant function. Then 0 plus f is just going to be equal to 0, or the number, it's because in this case I'm just letting 0 be 0, so 0 plus f of x, but anything added to f of x is just going to keep it f of x. Sorry, whenever I add 0 to f of x, it's just going to keep it f of x. Anything added to 0 is itself, so that's just f. For number 5, we need negative, so let's let minus f be equal to minus f of x. So then we have f plus minus f is equal to f of x plus minus f of x, and that's just 0, which is the 0 vector as we defined it. Let's let 6, well, remember this is the same as number 1 in this case, the scalar multiples of functions defined at each x in the interval from minus infinity to infinity are still going to be defined at each x in this interval. Same reasoning, multiplying a function by a scalar isn't going to make it undefined. Let's look at distributive property now. So k times f plus g, that's just going to be k times f of x plus g of x. Oops, forgot to close my parentheses. And that's just k times f of x, because we can distribute scalars over function addition, plus k times g of x. So that's kf plus kg. Okay, how about number 8? K plus m times f is going to be equal to k plus m times f of x, which is k times f of x plus m times f of x, because we can distribute the scalar now, and that's kf plus mf. Number 9, k times mf, we need to show it's associative, so that's the same as k times mf of x, which is associative, so that's km times f of x, and then we can go back to kmf. Okay, last but not least, we have 1 times f is just 1 times f of x, which is just going to be f of x, so that is f, so 1 times f is f. So this set of real valued functions under the normal addition and scalar multiplication is in fact a vector space. about we let v equal R2, and we define addition and scalar multiplication as follows. So we'll have u plus v be u1 plus v1, u2 plus v2, so addition is normal, but scalar multiplication is just multiply that first component by the scalar and just make the second one 0. So anytime you take a scalar or multiply it by a vector, your second component gets obliterated. So to show this thing's not a vector space, we just need to show that at least one of the axioms fails. Let's look at the first 5. Notice those are all just pertaining to addition, which is just the usual addition, so all of those must still be true. So they hold because we have the usual addition. So let's look at number 6. If we take k times u1, 0, that's just ku, then that's going to be an R2. So 6 holds, because it doesn't matter that there's a 0 there. It's all the vectors with 0 in the second component are vectors in R2. Okay, how about scalar multiplication? So we have k times u plus v. So that's going to be k times u1 plus v1, u2 plus v2, and that's equal to ku1 plus kv1 with a 0 for that second component. When we move in the scalar, this guy gets zeroed out because of the definition they gave us. So then we can split that using addition as ku1, 0 plus kv1, 0, which is in fact ku plus kv. Okay, so 7 works. Let's see about 8. So we have k plus mu. That's equal to k plus m times u1, u2. But that's just ku1 plus mu1 when we multiply it by u1, and then u2 just becomes 0. So that's ku1, 0 plus mu1, 0, which is still ku plus mu. Alright, so that works. How about k times mu? So that would be k times m u1, 0, but that would just be km u1 times 0, which is kmu, so that works. So hopefully 10 fails, otherwise this thing's actually a vector space. So let's take u equal to u1, u2, and let's say that u2 is not equal to 0. So then if we take 1 times u, we'll get 1 times u1, u2, which will be u1, 0, because anything has to get 0 in that second piece. And notice that's not equal to u, because we said that u2 is not 0. So for example, if you took the vector 2, 1, and you multiplied it by 1, then the 1 would become a 0, so it wouldn't be the same vector you started with. So it fails because you can't multiply any vector by 1 and still get the vector that you started with. It just fails because of axiom number 10. It's interesting how close this thing was to actually being a vector space. For our last example, let v be the set of positive real numbers, let u equal u and v equal v be any vectors, that is, positive real numbers in v, and let k be any scalar. define the operations on v to be u plus v equals u times v. So what we're saying is when we add two numbers, what we're really doing is we're going to multiply them instead. And scalar multiplication to be u to the k for ku. So when we multiply a scalar times u, we're going to take u to that scalar power. So let's confirm that v with these operations actually is a vector space. So just to, be an example, if we take 1 plus 1, in this vector space, what we're really doing is we're taking 1 times 1. So that'll end up actually equaling 1. If we take 2 times 1 in this vector space, then that'll be the same as taking 1 to the second power, 1 squared, which is 1. So this is a very weird vector space. How about we confirm the axioms now? For number 1, notice if we take the sum of any real numbers, what we're really doing is we're taking the product of, this is positive, only positive real numbers, and any product of positive real numbers is still going to be a positive real number. So the product of positive real numbers is a positive real number. So this thing is actually closed under vector addition, which in this case is regular multiplication. Let's look at commutativity of it for addition. So if we take u plus v, in this case that's u times v. So remember, regular multiplication is commutative, so that's just that's just vu. We could just switch that order, which is v plus u. So it is commutative. Let's look at associativity. So u plus v plus w. Well, that's the same as u plus vw, because that's what addition is. So that's the same as u times vw, because that's what this addition is. And then regular multiplication is associative, so that's uv times w, which is uv plus w for this multiplication over here, which is the same as u plus v plus w. So it should make sense that addition is associative because regular multiplication is associative. How about we take the 0 vector in this case to be equal to the scalar number 1? Notice that'll work because if we take u plus 1, that's u times 1. So that's just going to be u. Weird, I know. So for minus u, the reciprocal will have to be the multiplicative reciprocal. So we'll make that 1 over u. Notice then u plus 1 over u is going to be u times 1 over u, which is 1, which is good because remember 1 is the 0 vector. So just to remind you, that's the 0 vector. So u plus its negative will in fact be 0. For 6, same as number 1, the power of a positive real number is a positive real number. So this thing is closed under scalar multiplication because it's closed under exponentiation. Now let's take a constant times u plus v. So that's uv to the constant power. But the exponent come out by properties of exponents. So that's u to the k times v to the k by properties of exponents, which is just ku plus kv. For number 8, let's look at k plus m times u. So that's u to the k plus m, which is u to the k times u to the m by properties of exponents, which is ku plus mu. For number 9, we have k times mu equal to k times u to the m, which is u to the m to the k, and then by properties of exponents, that's u to the km, which is just km times u. Last but not least, if we take 1 times u, that's u to the 1, and by properties of exponents, that's just u. So this thing actually is a vector space. Pretty cool. We'll conclude by mentioning that if V is a vector space and U is a vector in V, K is a scalar, then 0 times U is the 0 vector. So if we take the scalar times U, we'll get the 0 vector. We didn't formally state that we required that, but it follows as a consequence of the other axioms. K times 0, so any scalar times 0 vector will also be a 0 vector. If we take negative 1 and multiply it by U, then we'll always get the negative U vector. And if ku is 0, then k must either be the 0 scalar or u must be the 0 vector.